Okay, last time we discussed the evaluation for the classification using computer matrix, and we also use the cost and the benefit to include the ideas of the beneficial and financial information so that we can evaluate the cost to the whole activity. Now we continue the ideas of the oversampling and asymmetry. The asymmetry cost idea is to focus on the rare case, but they are important. Actually, we have ever discussed this the rare cases. In that situation, we use the oversampling for rare case so that we can increase the rare case numbers by applying the weight to the rare case in the sampling equation. Usually we set 50% for Y and 50% for 0 for the training sampling. But for the rare case, like the applications and sending email to responders, the responders have less amount of the cases, and most will not send back the email or mail. So like the naive rule will treat the normal case just 0 response. Yeah, if we have response, just treat as error. Here we have the 3 methods for the treatment of the rare cases. Yeah, first one, we assign the same cost for different classes. And for the class 0, class S, in the left figure, and we can obtain the classification results. The classification line is one vertical line. The misclassification will be 2 circles on the left. So the cost will be 2. Yeah, 2 arrows. The right side using a second strategy, assuming the misclassification O is 5 times the cost of misclassification of X. So if we continue use the left one figure, the total cost will be 5, 2 times 5 will be 10. Yeah. On the right side one figure, this new classification, the misclassification will be top 2 X. So the total cost will be 2. So right side one division will be better according to the new policy, assigning 5 times cost for basic classification of the O. A third method is to apply oversampling of the case, the class O, 5 times more than class X. Yeah, so you can realize the equivalent performance of assigning 5 times cost for the misclassified O. So we can get the results in this one figure. This oversampling will assume the cost for misclassifying X and O the same. Both are 1. But the sampling of the O will become 5 times more. Yeah, become 5 for Y O. And for this one division, we can see the misclassification is 2x on the top. So the cost is 2. Yeah. Okay, the oversampling method can be realized using the strategy in this slide. Firstly, we can separate the responders cases from non-responders. This will be the AQ1 for the responders. Non-responder will be AQ0. So we can divide the samples according to the AQ responder. Then we randomly assign the half responders to the training set. So the other half of the responders will be in the validation set. Yeah. In the training set, half some cases will be the responders, half cases will be from the non-responders. Yeah, 50% AQ1 and 50% for AQ0 in the training set. So in the validation set, we have 50% responders already. Okay. Then we add a non-responder cases to the validation set to maintain the original ratio of the responder to non-responder. So this original ratio will be 50% to 50%. Yeah, so that we can equally treat the rare case for the HU1 case. Yeah, from original very rare now become equal weight. Then we can create the test set from the validation set. Yeah, we make a randomly sampling from the validation set. Yeah, so this actually.
Hey, Dr. Wayne, I'm sorry. Can you go back to slide 62 or go back 2 slides?
Okay.
I wasn't quite following the examples that you had. So if you look at the example on the left, when you look at the classification, equal cost of 0 equals 1, and cost of X equals 1. I don't understand why you have cost of 0 and cost of X, that both of those equals 1. Can you explain that again?
Okay, this the equation is for the misclassification cost. If you make a wrong classification for the O, the cost will be 1. You have a wrong classification of the X, the cost is also 1. The division that the points of the S and O is the original root data. Okay, the division, if we make a division line at this one location, vertical line, and so the right side will be class O, left side class X. So on the right side, all are correct. Yeah, because O is for the class O. This is correct. Left side, there's two wrong classification. Two O are wrongly classified to be X. Actually, there are O. So there are wrong classification for the O. So the cost will be 2. The one cost is 1. There are 2 O will be 2 for the misclassification.
I'm sorry, where are you getting the 2?
Oh, there's a 2 here, is the 1, and the 2. Oh, sorry. I can't. Oh, sorry, it's 1. Sorry.
Okay, that's what.
It's my screen
Okay.
problem. My screen is 30. Sorry. Okay, it's 1. Yeah, misclassification just 1. So cost will be 1.
Okay.
Yeah, sorry. My screen is 30. Yes.
Got it. Okay.
Yeah, so the cost, total cost is 1. The right
Okay.
side, yeah, right side, there are 2 X is misclassified.
Okay.
So the total cost will be 2.
Thank you. That helps.
Yeah. If you use this, the policy for the misclassification of O to be 5, the left side, the total cost is 5. Yeah, 1
Okay.
O is wrong classification. So the cost on the left will become 5. Right side is 2. So the right side division will be better on the new policy.
I see. That makes sense. Okay.
Oh, sorry
Thank
about
you.
this.
Nope, no problem.
But my screen the dots on the points. Okay, sorry. Yeah, do you have any other questions?
Thank you.
Yeah, so we continue. Okay, so we can realize oversampling based on this slide, so that we can obtain the same number of the rare cases as the normal case and a normal class. And before that, we have to increase the rare cases in a data set. Yeah, that's the like this one slide. Yeah, originally just 2 dots, now become 10 dots, 10 cases. Yeah. After that, we can make the policy of this slide. We can obtain the same number of responders and the same number of the non-responders for the training set, and also for the validation set. So here we have questions in the oversampling procedure. How many responders do we randomly assign to the training sample? Plus equal number of the non-responders, while the remaining responders go to validation sample. Yeah, how many responders to the training sample? Yeah, actually it's 50% responders to the training and another 50% for the vegetation set.
So this had the 50 and 50,
Yeah.
but would in this particular example for the oversampling, didn't that go to 10?
10. Sorry, why you say 10?
Well, so I was looking at slide 63. If you go to 63,
Is okay.
based on the example,
Yeah.
then the oversampling went from 1 to 5, but you have a total in this example of 10. So one block, you have 5, and then on another block, you have another 5, so a total of 10.
Yes, you're right. Before this procedure, we need to increase the rare cases for the sampling. Yeah, then we can separate. Okay, we can assign half responders, 50%. Yeah,
Right. Okay.
Yeah, responders for the training, and the same number of for the non-responders.
Right. Okay.
Okay, we continue. Okay, this slide for the idea of the tri-age classification. These two make a classification, not just two classes. We will form third class. Yeah, not the C1, C0. Now we have the third class and comp between C0 and C1. This third category can receive special review because these cases are usually in a area is difficult to identify C1 or C0. It can be C1, it can also be C0, but it depends on the situation. Okay, this lecture we already discussed the evaluation matrix, comparing different data mining models. We can use a computer matrix for the classification. Before the computer matrix, we need to make the sorting based on the probability of the classification. Yeah, and based on this, we create the computer matrix. Then we will further to create the gift chart and the lift chart, or gain chart and the lift chart. Yeah. We further to create the decile chart. Yeah, lift chart, gain chart, and also create the decile chart. And we evaluated the cost and the benefits for the classification. Then we create the cost matrix and a profit matrix. And we also discussed the asymmetric cost, yeah, for the oversampling. We also discussed the other metrics based on the computer matrix. We have the error rate, accurate rate, and also the precision and the specification, specialty. Yeah, F1 score, etc. Actually, this matrix usually computed based on the validation set. And because the training set is for the question of the model. Then we apply this model on the validation set to evaluate the performance of the model. Okay, this is the module 5. And we can go back to the Blackboard to see the assignment for this class.
And Dr. Wayne, when we look at the assignment for this, we're going to still use Jupyter Notebook, right?
Yes, Jupyter.
Okay.
Yeah.
Okay.
You can use the Colab. Either way, it can work.
Oh, okay. All right. Yeah. Thank you.
So this quiz due March 21. You have 4 days. You can finish this week. We continue next one later, module 6. Module 6 for the multiple linear regression model. Actually, we discussed this model in module, I think in module 3, data mining procedure. We used the linear regression model, but we will continue work on the model and apply more analysis for the methods. So, okay, okay, multiple linear regression model is one combination of two methods, explanatory and prediction. The explanatory is one process to fit the known data, known output. And we know the output and try to train in the model to make the prediction of the output to be small, a minimum error. Then we can use this trained model for the prediction. For the prediction case, there's no outcome. It will create one predict outcome. So that's why we call this a multiple linear regression model. In this lecture, we will discuss multiple linear regression model using the dataset of Toyota Corolla. We will evaluate the prediction accuracy using the error between the prediction and the actual value. It will be the error rate or accuracy rate. And we also work on the analysis of the number of the predictors. We find some predictor is not necessary, have the weak contribution to the outcome. So we can consider to reduce the number of predictors to realize the same performance for the outcome prediction. In a linear regression model, if the input parameters, input variable is just one, so the output variable also just one variable. So this just one linear regression model. It's a simple linear regression model. And the approximation for this model just one line between two variables. You can draw this line in a 2D plot, just one slope and the intercepts for that line to realize minimum error of the prediction. In the actual case, there are multiple predictors for the input and one the outcome for the dependent variable. So there we have one equation in the figure in the bottom. The y is for the outcome. It depends on the right side. The right side has parameters beta 0, beta 1, also until beta p, and also the predictors from beta S1, S2 to SP. So the S1 to SP will be the predictors as input. And beta 0 is one constant, just like the intercept in the plot. Beta 1, beta 2 will be corrections for individual predictor. The E will be the error for the prediction. And we try to realizing the minimum error in the model training. So here are questions if two or more explanatory variables have a linear relationship with a dependent variable. What is the regression called? So we have two or more explanatory variables, two or more for the predictors, and one dependent variable for the outcome. So this is a multiple linear regression model, not a simple linear regression model. In a multiple linear regression, what is a dependent variable? This dependent variable will be the outcome, the y.
The y. Mm-hmm.
Y.
Right.
The last one, what establish the relationship between two variables using straight line? Will be two parameters. One constant, that is the intercept. The other one is the slope. The slope is one quotient for the variable. Similar, just one for this. We only have one variable S1, and the others S2 and P do not exist. So only two parameters, beta 0, beta 1. Beta 0 will be the intercept for the constant, and beta 1 for the correction or slope. So the two parameters for the simple linear regression model. Okay, we continue. Okay, this slide for the explanatory modeling. This actually to explain the relationship between predictors and the target. The target is the outcome. Will be the input and the output. You can build this relationship by creating the equations beta 0, beta 1 until beta p. So the target is known. So this is for the training. Training the target is known. So this is the explanatory process. Because this one fitting process to fit the data well. to realize the minimum error for the outcome, so that we can understand the contribution of the explanatory variables, predictors, to the model. From the this one equation, the high equations will mean the contribution for the variable is high. Even a small change of the variable can realize big change to the outcome. So that we can learn the correlation between outcome to the predictors. The high equation would be high correlation for the two variables, the outcome and the predictor. Okay. So we call this goodness of fit, R2, or residue analysis, or p-value. So that we can realize that the error p percentage, minimum, the smaller the better. The R value is between -1 to 1. It will be the correlation. The R square value will be replaced with the R square, the square of the correlation. So we try to measure the proportion of variation in a dependent variable that can be contributed to the independent variable, and try to realize the smallest error E in this equation. So the question beta 1, beta 2 will be similar to the correlation questions.
Hey, Dr. Wayne, if you were saying
Yes.
something, we can't hear you.
Okay. Oh, sorry. We continue the next one slide.
Oh, okay. Thank you. Mm-hmm.
Okay, the first step is explanatory modeling for the training. Because in that case, we have the target known, so can realize the smallest error in the training. We call this fitting the data. Then we apply the model to the validation set or test set, test data. And this will be the predictive modeling. In this case, the target is unknown. We only know the predictors. So we can evaluate the prediction accuracy by comparing the prediction error to the actual value. So here we have questions. What is the goal of explanatory modeling? Who explain? The goal is to fit the training data to realize the minimum error in the explanatory modeling. Yeah. Second, the goal of the predictive modeling to predict. So this predictive modeling to make a high accuracy of the prediction. This case, we don't have the outcome. Okay, next one, what's the model goal of explanatory modeling to do?
That isn't
Yeah.
that supposed to explain the
Yeah.
relationship between the predictors and the target, which
Yes,
the
you're
target
right.
is known?
Yeah, target is known. Yes.
Okay.
Yeah. So last one, what's the model goal of the predictive modeling is to do?
Predict target values, where the predictor, well, we know the predictor values, but we
Yeah.
don't know the target values.
Yes, you are right. Yeah. Right. Yeah. Thank you.
Mm-hmm.
Okay. Next is for the example data using multiple linear regression model. This data is a Toyota Corolla data set. We use this data to predict the prices for the used Toyota Corolla car based on the specification as a predictor input. In this data set, there are 1,000 used Toyota Corolla prices and along with the specification information. So that we can train the model for the prediction of the price of one used car. In this dataset, we have the variables included here, a price expressed with units, euro, dollar, and the age is for the creation date for the car, kilometer used, fuel type is diesel, petrol, and CNG. Yeah, there are three kind of fuels. So this is the one critical variable. HP horsepower, metallic color, yes or no. So this one dummy variable. Automatic transmission, also one dummy variable. CC cylinder volume, doors, it can be 2-door, 4-door. Quarterly test will be road test. Road test. Weight will be the unit, kilogram. So we have the example data sets in this one slide. The price, age, kilometer. You can see the fuel type can be the diesel or petrol, and also CNG. Yeah, CNG is not expressed here, but also can be chosen for the fuel type. Horsepower, yeah, it's one range value can be 90, 69, so it's a numerical variable. Metallic is one dummy variable, can be 0, 1. Atomic also dummy. CC is one variable, numerical variable. Doors can be 3. Here there's 3 doors. It's weird. I think it's just option number. It's a critical variable. It's not a real. Usually just 2-door or 4-door. It's not 3. So I think this is not the real value for the doors. It's just one critical variable. Quarterly test can be range value, numerical value, weight also numerical. Yeah. So we can put the price as the outcome. And the others can be the predictors as income. Yeah. And
I'm sorry. So you said in this example, the price will be the outcome or the Y, right? And everything else will be a predictor.
yeah, others will be income as predators.
Okay.
Yeah, on the right side in the equation.
Got it.
Yeah, so you can see we can make a pre-processing to convert the critical variable to be dummy variable. In the previous slide, we can learn that the field type with 3 options. So this one critical variable so can convert to the dummy variable. Here diagonal patrol we have a diagonal one dummy variable, patrol also dummy variable. For the third category, CNG will not create a new class because both diagonal 0, patrol 0, the both 0 will be for the category CNG. Yeah, both 0 will be CNG. So we just create 2 dummy variables. Yeah, for the categorical variable field type. Now you can also create the 3 dummy variables. Yeah, you can change the parameters for the categorical function. Yeah, it's got one option to create the m-1 dummy variable or m variable, depending on your choice in the parameters. Here is the code. Beginning will be the import of the package from the data mining. And then we import the data from the dataset using function pandas package and read CSV function. Okay. Then we create the predators. Actually, we discussed this already. We define the predator as input variable. We just make a list of the input variable name. Yeah. We define the outcome. The outcome only has one variable, the price. Okay, the other will be for the input for the predators. Okay, then we convert the dummy variable to categorical variable, dummy variable to the, sorry, we convert the categorical variable to the dummy variable using function pandas package get dummies. Okay, the data input data will be retrieved from the predator list. For the conversion categorical variable to dummy variable, you can change the parameter for the draw first. Yeah, if you use the draw first true, we can create the m1 dummy variable. If you draw first false, sorry. Sorry. Yeah, you can change the parameter draw first to false. Then you can apply m dummy variable. I mean, the number of dummy variable will be the same number of the categorical values for the categorical variable. Okay, then we create a y for the column outcome variable. Okay, so we have 2 data sets, S and Y. S is for the predators, Y for the outcome. Now we call the function trend test split. Okay, in the train test split function, we can change the test size to different value. Here is 0.4, but that means 40% for the validation set, 60% for the training set. So this value smaller will be better for the fitting results. Yeah, more data will be used for the training, the smaller value for this test size. Then we define the random state. That means the selection for the training set and the validation set is randomly. Then we call the linear regression model. Okay, then we start training. You calling the function fit on the training data X and the training Y. So then after the fitting, we can obtain the training result. This is why function will be time consuming. Yeah, if the data very complicated, this will be very slow. The fitting is slow process. Is one kernel part of the data mining for this equation. But after fitting, we can obtain the fitting results for the training results. Yeah, we can obtain a S column. This will be the variable name for the predictors input variables name. Let's the column. And the car online RM will be the the model, the trend model. We using the .coef to return the questions for individual predictors and also one questions for the constant. Yeah, so we can obtain the results in this way table. Okay, the age has a correction -140. Km is 0.017. Yeah. So you can see the field type, patrol and diagonal has the highest, patrol has highest weight. So the price of the car is depend on mostly on the fuel type. Yeah. The car, yeah, usually our car use a gas. We seldom use a diesel. The diesel usually for the truck. Yeah, so we can understand that. And also the automatic car is widely used. Yeah, the manual car is seldom used. So this also good weight for the price. Okay, the edge is too old, the price will be low. Yeah, the edge is small, the price will be high. So it's also makes sense. So we can obtain a correlation to the outcome variable, yeah, which has a high correlation, which has a low correlation from the coefficients. Yeah, so the coefficients will be replacement for the correlation coefficients. Okay, we call the function regression summary on the two datas. One is the training Y. So this is the outcome from the the outcome of the training set. This is the actual value for the outcome. Okay, the other one is the using the predict function from the model on the training set X. So this is the prediction result, prediction value. So we can compare the prediction value to the actual value for the outcome. So we can obtain the regression summary. The results will be on the bottom. So we can see the mean error will be almost 0. The root mean square error, 1,400. Yeah, we can also see others. So we can obtain the matrix usage on the training data set. So we can see whether it's good or not to compare different models. And we can create one data frame using 3 data. One is the predicted value using the predict function of the model on the validation set. Okay, the second column will be the actual value for the validation set outcome variable. Okay, then third column will be the residue value. Will be the error between the two data, the validation, the real outcome for the validation set. The other one will be the predict value for the validation set. So we can get the results on the bottom. The right side will be the error between the previous two values. Okay. Yeah, so we have the pretty actual. Yeah, so we have the predicted value here. So we can use the validation set outcome value to the predicted outcome value to create the regression summary. So okay. This slide for the regression summary on the training data set and the predict value for the training data set. Okay, this slide will be for the validation data set. So the mean error about 103. Yeah. This mean error is larger than the previous one slide because previous one slide based on the training results, training data. The training data is one treating process. Yeah, it's one explanatory model. Yeah. So the error will be smallest. That's why the mean error almost 0. But the validation set it does not use the outcome of the actual value. So it has big error for the prediction. So the this regression summary is on the prediction model, predictive model. Yeah, outcome don't know, just make prediction. Then compare predict results with a real outcome. So there's one deviation very big. So here we can question which function can convert character variable into dummy or indicator variables. which is one function. And can you remember? Yeah, it's actually that function is from the dummy, from the pandas package. Or the yeah, dummies. Yeah, dummies. Is here. We'll get dummies, pandas get dummies function.
So you're saying that the dummies function in pandas, I see it.
Yeah.
Get underscore dummies. Okay, I see it.
The PG from pandas package.
Yeah.
Okay. So we continue next.
Okay.
Then we discuss the selection of the subsets of predators. For this one example code data and code, we have only small number of predators. But in a real situation, there are more than this, maybe even more than 100, even 1,000 predators. And for the large language model, like the DeepSeek or ChatGPT, they use about 1,000, even million predators. Yeah, for that case, you have too many predators. The training process very slow, maybe several days, even several months for the training. To realize the best performance, we can reduce the number of predators. Yeah. But if you choose the small number of predators, is one trade-off process. Yeah, so here we will discuss this how to realize the same performance, but we can use smaller number of the predators for faster training. Here we assess the predictive accuracy on the validation set. We already know this in the previous slides. We can realize this subsets, the best subsets for the prediction. We use the exhaustive search. And this will be trying all the possible subsets to compare which one is the best. Yeah, this one's, but this is very tedious process. Yeah, everyone possible subset we have to train the model and obtain the summary, and obtain the mean error, root mean square error to compare which one is smallest. But we have other algorithm, a partial search algorithm, to obtain the same results. The first one is the forward algorithm. The second is backward, and the third one the stepwise. Yeah, forward I mean we choose from 0 predator, then we add a predator for one time. And we choose from beginning one variable, then get the prediction results, then add the second variable, and to see which one second variable is the best. Yeah, so finally we can reach the final the best one choice. The backward will be opposite direction. We are starting from all the choices of predators. And then we start to reduce the number of the predators. Yeah, we will try to reduce the variable that not affect the accuracy. So each time just reduce one predators. But stepwise will be two direction. Yeah, can be forward and backward. We will discuss separately. So there are 4 methods: exhaustive search, forward search, backward search, or stepwise search. For the exhaustive search, we will obtain all possible subsets for the predictors. Then use the intensive computation to obtain the best one subset. We will use the metric to evaluate which one is the best. We use the R square, adjusted the R square, 1 minus n minus 1 divide 1 n minus p minus 1 times 1 minus R square. P is the penalty for the number of predictors. So we can call the reg subset function in the package libs. And we will check this in the code later. Okay, this slide about the code of the exhaustive search. First one function is the training model. Yeah, the parameter, the variables. We create one model for the linear regression. Then we train the model on the training data X and the Y. And you can see the training X has the flexible input. It's defined by the variables. The variable will be different for different subsets. For the second function is score model. It has parameter model and variables. Okay, the first line it uses a prediction function on the training data. So we get the prediction results. Then we compare the training Y and the predicted Y. Okay, this has error deviation. Then we use these two data to calculate the adjusted R square score. Okay, then we have all variables for all the training data predictors. Okay, then use this all the variables for the predictors to the exhaustive search function as input for the exhaustive search. Then we call the function train model and score model to realize the exhaustive search definition. Then we can compare the results. To evaluate the performance of different subsets, we can just now we use the adjusted R square score. We can also use the AIC score. AIC is for the abbreviation of the archaic information criteria. The lowest AIC score will be the best model. And so we try to realize the smallest AIC score. The RC score is calculated using this equation n times the log function, logarithm function. Then residue sum of the squares divided by n. Okay, finally we add the 2k, 2 times k. In the number of observations will be number of cases. The k for the number of parameters, including the intercepts, to be the number of predictors plus the intercept. So we can modify the code. We call the for loop. Results in the results. So we will iterate individual results. For the model column of the result, we get iterated model, and we will also obtain the variables for data calculation results. Then we calculate the LRC score for the training data output and predict the output using the predictors defined by the variables in the current calculation. Now we build a Z frame using the column N. The R2 R square adjustment value and the RC value. Sorry. Okay. I'll continue. Here, we create the data D using the three data, the in value, R2 adjustment value. This obtained from the results score column and the RC score calculated using RC score function. Yeah, based on the training data set outcome value and the predict outcome value for the training data. And we updated the data G. For the variables, we add all the variables in the data D, and the value for individual variable using the logic value, yeah, whether this variable, the inner used variable in training, yeah, in the fitting, yeah. Because this is from the fitting results used for the fitting result variables. If inside here, it will marked with 1, true. If not inside this list used for the training, will be marked with false. Now we add this d value to the data. So for every time searching for different subsets, we have new results added to the data frame. Okay, then we build a new data frame using the data. So we have the column name with in is from the D definition here. In R2 adjust ARC. Then follow with the variables. Yeah. So variables value will be true or false. Yeah, depending on whether used in a search, exhaustive search subsets. So we can get the results like this one figure. So you can see the in column and then R2 adjustment RC. Yeah. So we define here in the D. And also we have the individual variables in all the variables from the predictors original data. And according to different different search, different subsets, you can see the variables has value true or false. True that means that variable is used for data search. Yeah, if it's false, that means that variable is not used for data search. Yeah. Do you have any questions for this slide? Yeah, so you can see this exhaustive search will try all the possible subsets. Yeah, for the zero case, the n is 1. That means that there's only one predictor. The only one predictor will be the age. Yeah, the other will be false. All other are false. Okay, for the case the n is 2, that means there are two operators. Okay, one is the age. The other one is the HP. Yeah, horsepower. For other will be false. Okay. Yeah, so You get this. Okay, the second choice. Okay, this is the exhaustive search method. Okay, the second is the backward elimination method. It starts with all the predators. Then we start eliminate at least one predator and try this way until there's only one predator. And then we'll stop when all remaining predators have statistically significant contribution. Yeah, if you continue reduce this IC score will not reduce anymore. If you continue reduce the predator, the IC score will become increase. Yeah, here the code for the backward elimination using IC score. We also have the two functions, a train model and a score model. The train model is the same before. We'll create the linear regression model, then train model using a fit function on the data training data and validation training S, training Y. Training S will be partially from the variable defined in the input arguments. In the score model, we use IC score. IC score will be applied on the two data, training outcome, original actual value for the training Y, and predicted Y. Predicted Y using training data variables. So we can call the function backward elimination. The first one parameter will be all variables. Then we use the two functions, training model and score model. The verbose is enabled with true. So we want to see the detailed information during the training process. So then we call the regression summary on the validation outcome and based on model prediction on the validation set. Okay, this is the execution results. So here we have the variables list, and we start from beginning because we start from all the variables. It has score 1, 0, 4, 2, 2, 3. Then we reduce first one variable CC. We obtain IC score 10, 4, 2, 0. Okay, we continue reduce metal color. We can obtain the 10, 4, 1, 8. Okay, so the IC score become smaller. Okay, then we remove those dots. The value is 10, 4, 1, 7 to 9. And we reduce 9. Oh, yeah, we not reduce anymore. We can't. We just stop here and we don't reduce any variable anymore. So the best IC score will be 10, 4, 1, 7. So then we obtain a regression summary for the statistical calculation between the actual value y and predicted y. So the error for the mean error is 103. And root mean square error will be 1314. Okay, second, the third method is forward selection, starting with no predictors. Every time we just add one variable that can have largest contribution, and stop when the addition will not statistically significant. I mean, we'll stop when the IC score will not reduce. Okay, so it's similar to the backward selection. We have the function train model and a scan model or score model. In the train model, we add one statement, if statement. If the variable length is 0, then we return with null. Null. Because it starts from 0. Yeah, so the 0, the variable number will be 0. Yeah, so the starting point will not continue of the train model. Also change the score model when the starting point variable number is 0, will return the default IC score. When we call the function forward selection, we use the parameters for all the predictors and two functions, train model and score model. The verb was enabled. Yeah, then we print the return the best parameters, best variables. So you can see from the record, we can learn it start from 0. The IC score is 11565. When we add the age, the IC score reduce. Add LP was continue reduce. And add weight, KM, etc. Until we add the automatic, the IC score reach 10417. Then we will continue to add the other variable. This value, IC score, will not continue decrease. So we just stop here without any adding any extra predictors. So finally, you can realize the collection of predictors, the best predictors. There are 8 predictors. The last one method is stepwise. This is similar to the forward selection, but at each one step, it also consists dropping non-significant predictors. And we can compare this above several methods choosing the predictors subset. We can see the final best model, best parameters are the same. The forward, backward, both exhaustive. They can realize the same choices of the subsets. But the exhaustive is slowest one, slowest method. Yeah, usually we can choose the forward or backward. Both the stepwise is not provided in detail. So we try the forward and backward. So here we have questions. First one, match the creator name to the method in or the selection or the subset of predictors. This is for the definition of concepts, forward selection, stepwise selection, exhaustive, and backward elimination. Yeah, so the fourth one, like forward selection, except at each step, consider dropping. So this will be the stepwise. Okay, the second, start with no predictors, add one by one. So this will be the forward selection. Start with all predictors. So this will be the backward elimination. Fourth, looking for the best subsets from all possible subsets. So this will be exhaustive search. Okay, so you can get this answer from literature content. Okay, regularization, shrinkage. This one method alternative to subset selection. It's not binary decisions on including variables. Yeah, it penalizes question magnitudes. Yeah, so it has the effect of shrinkage of the questions. So they can realize the same functionality to reduce the variables. Yeah, so the not important variables can be assigned with small weight, even 0 weight. The predictor with questions that shrink to 0 are effectively dropped. Yeah, so the equivalent to be dropped using the small questions value. So the variance reduction will improve prediction performance. Okay, the shrinkage ridge regression model. Here we use the optimal linear regression model. It minimizes the sum of the square error. So this method, ridge regression, minimize sum of square errors below the threshold value. With the penalty, the sum of squared quotients, yeah, we call the R2. In data penalty, the alpha is the penalty threshold. If the alpha is 0, that means there's no penalty. So the predictor will not be changed because we only change the questions. So the predictor will be standardized and will not change. So here with the code, the ridge function is called with parameter alpha equal to 1. Then we call the fit function to train the model. The data will be the training data S and Y. Then we call the regression summary on the true Y for the predicted set and all the predicted Y from the predicted model, yeah, on the validation set. So we get the results. Okay, the other way is a lasso method. Yeah, the previous slide showed the ridge regression, minimizing the sum of square error. and also consider the penalty. The lasso is called R1 penalty. It's the sum of the absolute values for coefficients. Here we set the alpha penalty threshold, and 0 will be no penalty. So we call the lasso function with parameter alpha is equal to 1. Use the same fit function on the training data. And then we use this model on the validation data X to predict the outcome and compare with the actual outcome for the validation set. So get the regression summary. Or we can also use the lasso CV function that use the cross validation. The cross validation is based on the idea dividing the data into several groups. And the K, and we have the K value. So we can go back to the data mining process. Yeah, yeah. In the 35 slide of the module 3, cross validation. Actually, we have the K-fold cross validation. We divide the data into K groups, K parts. Yeah, we will circulate this training data. Yeah, each time we just try one set. So we have K different training data set. Oh, sorry. It's one used for the validation set. The other K-minus one both are used for the training. So we have K different training data set. So that we can realize the best one training results using this K-fold cross validation. Now here we define the K number is 5. So there are 5 folders, 5 sets. For the cross validation. So we have questions in the shrinkage method, the ridge regression, what's the penalty? The ridge regression, the penalty is R2, the sum of the square error. So we can check. And the ridge is the penalty R2, sum of the square coefficients. Okay, the other shrinkage, lasso, use R1, sum of absolute value of the question. Yeah, so this is the difference between a ridge regression and a lasso. The penalty are different. Lasso is just R1, the 1D just the absolute value of the questions. But the ridge will be the square of the questions. Okay, in this one lecture, we learned the multiple linear regression model process. It uses the category variable conversion to the dummy variables. And also, we use this training model to obtain the coefficients for the multiple equations, multiple linear equation, multiple linear equation. And we use the several methods to realize the best subsets. The first one is the exhaustive search. Then we can use the partial search, like the forward, backward, and stepwise. We can also use the shrinkage method for the choice of the subsets. Yeah, we will not change the predictors. And we just assign different questions for different variables. So we have two methods. One is the lasso. The other one is the ridge. Ridge is the R2 penalty. The lasso will be R1 penalty. Only the sum of the questions. Yeah, do you have any questions for this one lecture? Now, actually, we have one assignment, lab assignment for this one lecture. So 6. On the lab is here. And it's due end of this month. Now, so next week. So you can open the assignments. This to work on the data with Raspberry. So we already tried this example in module 3. Yeah, we can define the predictors, except total value and the test. Yeah, the other will be the predictors. The total value will be used for the outcome, output. And we set the division ratio 50%. 50% for validation, 50% for the training data set. We also use we also need to transform data category variable to dummy variable. They're called the get dummy function. So we train model, then we can obtain the intercept value for the questions. And also we can obtain R2 square values. We can also calculate the RC score values. And we can try the exhaustive search method to obtain the best subsets and corresponding lowest RC score. And we try also the backward search and compare these two methods. And you need to submit the word file with a plot and one notebook file. Now you need to insert a name in the first line and provide Python code. You can use Jupyter, iPad, Python notebook file. You can download from the Jupyter or from the Colab or the Google. So you can obtain the model number maybe not great, it's 6, or maybe it's a 6. Yeah. So we can work together on this one assignment. So we can activate the anaconda. Mm.
I have a quick question, Dr. Wayne. So
Yeah.
the code, I didn't see the code in the zip file.
Okay, the code will
So,
be from the lecture, from here. From here.
oh, wait,
Yeah.
I'm sorry. Oh, okay, I see. Okay, got it.
Yeah, code inside here. So you need to download this first.
Mm-hmm.
Lecture zip file.
Okay.
Yeah, you are right. I need to add that file into the lab package. So I can extract these two files out and it's activated or not. I can't see it. Okay, still working. It's loading. It's slow. Here. Mhm. Okay. This will fly. So we launch. Okay. Yeah, this makes the arrow. So go to the directory. Then we drag the code here for the latest saving and the data here, the override. So we open the multiple linear regression. So you can see, yeah, or we can test it, just run a kernel, start kernel run all. So we see whether it's an error or not. So yeah, this code is from the collab. Okay, so uh, yeah, so this for the collab. Oh, sorry, this. I need to rename collab. Okay. Then we also save this. The Jupyter. Jupyter. The Jupyter will not use this dry mount. Save this. And we also need to update, remove the directory information. We look for all the read CSV. Okay, this is okay. Only one. Okay, we can already update this. We save it. Save all. Now start from beginning. Oh, so we need to disable all both. Now we start from beginning. Okay, so execute no error. So you can see it start here. Horizontal search is time consuming, and it finish. Then it's forward or finish. Yeah, stepwise to duration also complete. So you can review the code by your own self. I will upload this code to the Blackboard because the Blackboard code is for the collab. You need to remove the cell, the first one cell, you need to remove if you use the Jupyter. Because this edition for my computer, for my configuration of the Google Drive using a collab. So if you use Jupyter, you need to remove this one and also change the this one read CSV function, remove the folders for the data. Okay, so we can review this code. So we call the data using the read CSV. Then we define a predator for the input. We define predator outcome. Then you convert query code to dummy. Okay. Then we split the data to groups, training and validation. Then we train using the training data. Then we print the intercepts. Yeah, you can see the intercept is 1319, the native 1319. And the question for the individual predators is listed in this table. Okay. Then we obtain the predicted value. using this model for the training data. So we get the adjust R2 score for the active Y and the predicted Y. Yeah, and based on the model. And also calculate IC score, BIC score. Yeah, so the value is provided here. I score 10.422. But just R2 is just a small value, and 0.85. Well, you can try different metrics for the evaluation. Yeah, I think they are equivalent. Okay, then we apply this model for the validation data. So we can print the results for the predicted value and the actual value and the error, the deviation between these two values will be here in this table. Then we calculate the regression summary function on the predicted value and the actual value for the validation test. So the mean error is 100. Yeah, more than 100. Okay, next is for the residue error between validation, actual value, and the predicted value. This is to print the cases outside the range, the native 1406 and the 1406, divided by all the cases. So about 74%, 74% outside this range. Oh, sorry. The inside of this range, the larger the native value, less than the positive value. The inside the range will be 74%. Yeah, so outside of this range, it just within 1.4 will be here. Here, the major part will be 74%. The other part will be 26%. Yeah, about 26%. It's a Gaussian distribution for the residue. Okay, then we define a trend model function, score model function. Small model using the adjust R2 score. You can also use the AIC score. For you just replace the function name. You can replace with the different evaluation. And then call the exhaustive search function. So you can print output using the for loop for individual subsets. You can obtain the trend model and use the predictors. Then you can compare the predicted value and the actual Y for IC score. So you can print the IC score and also print the used variables for different subsets. Okay. Yeah, so for the n is 1, only edge is selected. Yeah, 2, the edge and edge P is selected, the other just false. So for the 3, the edge, edge P and okay, 2, okay, 3. Edge P and KM 3 are selected. Okay, next is for the backward elimination. Similar to the exhaustive search. Here it changed the R2, adjust R2 score. Adjust R2 score to RC score. You can verify which one, what's the difference between the RC score is a large value, the R2 score is one small value. Maybe large value is easy to compare. So you call back elimination for this way. Okay. And we can realize the mean error 103. Yeah, so be the same as the exhaustive search. Then the forward select also forward select start from 0. So add one line for the 0 number of variable, just return and will not process. Yeah, if we start from 0, yeah, I score just one value with a large, very large value. You can see the the train, the previous train, a very big value that times the number of the cases. So very huge value, huge deviation, right? Huge value for the IC score. So actually, this is not real. Yeah, this is just one fake value for the less 0. Okay, then we call the forward selection. Using training data S, the training model, score model function. Okay, so you can see you can either reach the final. The beginning is a very big value. Okay, the next is for the the shrinkage. First one use a lasso model using alpha 1. So we use a lasso model to train the data. Then make prediction, then get the regression summary. The next method using lasso CV. Lasso and lasso CV are using the R2 square of the questions for the penalty. The range just use the R1, the absolute value of the questions for the penalty. So you can see, compare the difference. So you can see the lasso 104 for the mean error, square root 1312. Use the ratio CV. It uses 5. K number is 5. The error become bigger, 114. And MSE is 3000, even bigger. Use the last one, reach. You use RY. So it has arrow a little bigger than the lasso. Yeah, so the best one, the best model will be the lasso. Yeah, lasso. Then will be the ridge. Okay, then last will be, okay, next is the basin ridge, basin ridge. Basin ridge, 107, 102, 1273. So what's the, okay, okay, worst will be the basin less ridge. The third is the lasso CV. Yeah, so best will be the lasso is best. Then is the ridge. So the modified method has lower performance, like the basin ridge or lasso CV. Because the lasso CV use small not sure why lasso CV equal to 5 has larger arrow. Yeah, so we can compare different methods. It depends on the data. Maybe some data is good to use the lasso, some is good to use lasso CV. It depends on the data features. Okay, so you can see the comparison. Then we output the comparison for different methods. So it's a comparison of the equations. Linear regression, lasso CV, and basin ridge. The lasso CV has small equations.
Quick question, Dr. Wang. You're going to provide the updated code
Yeah, I will
to use
upload
a
to the,
regular Jupyter?
yes,
Okay,
I will
thank you.
update. I will mark the difference of the version. The Jupyter will be for the Anaconda Jupyter.
Okay,
For the collab, changed the file name already. I add a collab here for the
yeah, because I tried to run it and I got an error message. So
yeah. So I will upload to the Blackboard. Because the collab is based on my directory, not your
okay.
directory. Usually it has error.
Yep.
So I will update to the collab version.
Thank you.
Yeah. Okay. Next is for train train data X joined with the train Y. So it will be the combination, the S and Y together. So we can build the formula. Okay, we build combine together to build the train DF data. Okay, then we create a formula, the price for the outcome, the wave operator is for the kind of like the equation, equal operator. The right side will be the equations on the right side. Then we plus the multiple predictors. Yeah, the group of predictors on the right side. So we call the model ORS model using the defined equation formula is here. Then use the data combined together of S and Y, then train the model. Then we print the summary of the trained model. And here, we have the dependent variable for the outcome. The other variable will be predictors. So this model is the ORS. It uses a least square error. So we have the number of observation, 600 for the records. So we have the 9. So here it will be the intercepts and the correction for individual variables. Yeah, there's this. Okay, we can do the homework now. So we can create the new records, a new file. That's the notebook file. And this means arrow. So we just copy the cells from the original code. So here we need to copy all the packages. Okay, I will upload now so you can follow me. So,
Okay.
Yeah, okay now. This and this. Yeah. So I also update this to the lab.
Okay, so it's already uploaded?
I'm working on it now.
Oh, okay.
Yeah, I'm updating now. Mm. Okay.
We should be able to open it up now, right? Because I think I just saw you upload it.
It's not correct. Fine.
I'm sorry, say that again.
It's not correct. I think I uploaded the wrong file.
Oh, wrong. Oh, okay.
It's wrong. Okay, that should be clear. Then you can download now. It's great. I uploaded the link.
Okay.
Yeah. Yeah, so we can continue on the code. So you can copy the package for the first cell. You can add a more cell and copy input the data the data for the which is assignment. It's from the worst Raspberry. So and this will use the exhaustive search. So the prediction of multiple linear regression model. So be same. So so we obtain corrections and also the R2 score, RC score. So we use almost the same code. Just copy the code. This is for the Toyota, but we will change it to the Raspberry. So change the data set to the West Raspberry. So just copy the file name here. But we need to know what's inside the data. What for the ink predictor, what are for the price. You can list one by one. Yeah, you can also use the method we introduced in module 3. In the module 3, we have the method to define predictors. So we open the module 3. Then mining process. So here we can, yeah, here we West Raspberry. So we can rename rename the total value which has a blank space. We remove blank space and change blank space with underline, and also change also other variable blank space with underline. Okay, we copy use this code on the Raspberry. We go to the here. Now, so we can rename the car DF with the housing DF. Maybe it's not necessary to just use 1,000 data. We can use all the data. So we rename. So just be careful. This character is not valid, and that's why it show error. So I can't copy directly. Okay, here we define the uh, variable name. Then we define the predators. the code in the ledger is not complete. We need to open the code file. That's 43, the get money process. Yeah, when the bar here, we go to the code.
Dr. Wayne, can you slightly reduce the size of your screen? It seems like some of the code is going off the page. I just think you have it zoomed out. Can you zoom in just a little?
Okay, this one?
Yes, that's better. Yes, thank you.
Okay.
Mhm.
So we can copy use this one. Yeah, to define the remodel to be critical variable and convert to be dummy variable. Here, get dummies. So you can define a prefix separation between the variable name and the different values separated by on the line. Draw first will reduce y variable, m minus 1. Yeah, so you can copy all the code. Yeah, it will reduce the null records.
Okay.
Yeah. So here we select okay, here. We we just copy this. Yeah. And then here and this before and this new. We will dummy variable and get dummy already processed here. Um, uh, define x to define predictor and outcome. So we have x and y. And here we have sy. Now here you can use 0.4 according to questions. And use 0.5. So you should change to 0.5 split. Then we fit the model. Then we call the corrections in the regression summary. So we replace the model name with a car and with the model. So get the questions. S and the model except the X is create the same columns. Okay, so we can run the code now. So we can get the output, the regression summary, the questions, and also we need to calculate the score. So score is here. We have the three scores. We copy it and we split the slide. We call this edit, split cell, and add a new cell for the score. Okay, so then what else? R2 score, RC score, and the next is exhaustive search method. So we call the exhaustive search method. Yeah, so we also use this for the visual comparison. So we so this model name valid as so this is not necessary. So we predict so, so this train predict. So this is not necessary. Then we continue to use the exhaustive search. Exhaustive search. We feel exhaustive search. We copy this cell for the exhaustive search and paste to the new code. So we need to modify. So okay, the data same, the model function same, the variable okay the same. And we will not change because the data same. The variables So all variables define. Yeah. So the code will not be changed, will be the same for the exotic search. Then we define for the exotic search finished. And Lewis I score the backward search. We get a backward search. Okay, this is backward search. So we print copy here, and also print the regression summary. So there's the summary. So then we complete the code already. So we can run the code now. Run from beginning, all the cells. No visual error. Let's see, okay, the data not available. So we upload data. This is the for the quest library. Because the this file is not in the same directory. So we need to save the notebook as so we save name. So save name as we define name. So it's the homework. You know, this is for the lecture 7, lecture 6. Homework. Okay. So you can see where it is. Inside. So you can see it's not here. Actually, it's in a root directory. So you can look for it. Let's see, look here. Yeah, we have to move this one file to the directory where the data exists. Okay, then we move already go inside. Okay, code here. We open it. We close the previous. Okay, this is the new node. Now we run again. Will be no error. Okay, no error. Oh, here has error. Okay, the model didn't change. The car model need to be model. Okay, we can continue. So also the model. We need to change the model name. And the others will be similar. Name, yeah. So we need to okay, that's here, that's here. So run it. So first one, is Y, is arrow. Okay, good. Ah, delete. Delete. Home. Let's see. Good. Okay, good. Yeah. So we finished the coding now. So we can analyze whether it's reasonable So as a load data, we change the variable name and we define predictor, outcome. Now get a split of data to groups. Then train model using the training data. Then we output the intercepts. The intercepts is negative 31. The corrections are here. Okay, then get the mean error almost 0. Then we calculate the score, adjust the R2 score 0.80. IC score is the 3105. And BRC is similar, almost the same. Then we predict the validation data, so we can get the 3 column predicted value, active value, and error. The error not big, it's fine. Yeah, and we try the exhaustive search. So exhaustive result here, we start from 1 parameter. Yeah, and we find the RC score. Yeah, decrease from 31445, then reach 3105. Yeah, then it will stop here. Will not increase. Will not decrease and decrease anymore. Will be 105. Yeah, 315. Okay, the R2 score. You can see R2 score will increase 53, 73 until 80, 64. Yeah, so R2 adjustment value will increase. The I score can reach the minimum value. Okay, the next is next is the backward elimination. So the start from a 30105 didn't remove anything. So it contains some problem. It can't reduce any. Yeah, all the variables. So I check my records I made it before. So this is my solution I made before. So it can remove stuff from here. You can remove 3 variables. So it has some. So let's check together. No square year built, gross area, living area, platform, score is different. I think maybe it has a pre-processing. This data on account and predators. Compare the questions. What's the difference? It's also different. Predators. There's how many predators? 12. Oh, the variable different. The model old is also used. Heating fireplace. Half full. Loss. The model old is used. The model fireplace model. Oh, I didn't apply the Carrigo conversion. That's the reason. Yeah, we didn't apply the conversion, dummy variable conversion. We should not apply dummy here. This cause. Yeah, so this not here because the predictor can't be seen for the fireplace. The model only recent. So we try to rerun again. Mm. Mm. Yeah. Mm. Okay, okay, I understand because data is different. Yeah, the my previous example used small data. I used 1,000. Yeah, here this code use all the data, so it causes different results. Yeah, if you use all the data, there's no reduction. Yeah, all the variable will be used for the best subset. Yeah, my previous result use a subset just 1,000 record because the exam code the exam code exam code Here, it used 1000. You can see it used 1000 data for the analysis. Yeah, that's why we can then adjust just number of subsets. Yeah, if we use a small data set, will be similar. Okay, we can change the small size. The small size data. Let's see what's the difference. Okay, now almost the same. Oh, still different. Mm. Yeah, from the small size data, it makes sense. You can see for the exhaustive search, you use exhaustive search, the IC score from beginning decrease and reach the minimum value at 8. Yeah. By 8, it becomes small. Then it increase with more size subset. So minimum, the best number of subset would be 8. Yeah. And for the forward, backward search, yeah, it is also similar results. The backward from high 4820 reach the minimum 4815. And it has also 8 variables: 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. 4819, 4815. The same 4815 here. Okay, here, yeah, 8, yeah, 9 predictors. The 9 is correct. So yeah, if you use different test size, it will have different results. It depends on how many data you choose. If you disable this, yeah, all the variables will be chosen. Yeah, any case, depend on your choice. If you use partial data, you can see the minimum value for the subset. Yeah, if you use the whole data, all the variable will be the optimal. Okay, do you have any questions?
I
You're
have.
gonna,
Oh, I'm
Okay.
sorry, quick.
no, you go ahead. I was just gonna make sure he's gonna post a video. That's it.
Yeah, I will upload video.
Thank you.
Okay, and mine I hope is quick, Dr. Wayne. Okay, so
Okay.
the dump when we be doing the dummy variable and assigning the dummy variable,
Yeah.
do we have to specify the variable that we trying to look for the dummy for, or is it automatically finding
Yeah,
the
it
variable to change?
yeah, it will identify the category variable and convert to dummy automatically.
Okay.
Yeah, all the category variable will be converted to dummy variables.
Okay, got it. Because that's what I was confused about. Because I kept trying to, of course, I was copying and pasting the code,
Yeah,
but I was
actually,
replacing the code, and I think I was taking too much stuff out and putting too much other stuff
it's
in.
better we add the Y 3-cell, make an analysis on the data. We can add a code here to display print house PF. We want to see the initial data. Okay. Let's see what it is. Yeah, you can We can run from beginning. Yeah. So yeah, all the data. You can also see the data type with just an example code, and you can see the type. Okay, so it's not type. Okay. Mm. So we can Google Python. Data. Choose. Let's see. Yes, D type. How to do this D type.
Okay.
Okay, D types. Oh, D types. Oh, so I lose my S. D types. Okay, so yeah, so you can see the data type for individual fields. Okay, total value,
Okay, yeah.
float point, yeah, then integer. But the last one, remodel. Remodel is object. Object is usually string. It's not a value. So usually they will treat it with the critical variable. Yeah, after the conversion, if we enable this conversion variable, the dummy, get dummies, we call this we split this cell. So before we show the data, and also we want to see the data type before the conversion. After conversion, we see the type, what changed. So we make a run. So before the data type is an object, yeah, for the remodel. After the conversion, you can see the remodel have been converted to one dummy variable, the bool type.
Okay, yep.
Yeah.
Got it.
Yeah, automatically change the object type. Object type is a string. That's usually treated as a critical variable and convert to dummy variable directly.
Okay, thank you for explaining that,
Yeah.
Dr. Wayne.
Yeah, you're welcome. So if you convert dummy variable beginning, you can yeah, actually it's better do it separately. When you choose the X, you can convert. It's not good. Do it at beginning. So we just remove this. Enable this. Remove. Delete this. Okay, so we split here. We get now we predict x. So we can do this way. Predictors S predictors, then we print the S type, then the dummy X. Okay, then we return the S. So we split cell here, split, okay, then print results. Split again. So we can run from beginning. Yeah. So just create an initial value. Then we, yeah, you can see X, all the variables. The last one, remodel, is one object type. It's one, actually it's one categorical variable. And run, we convert the X. The last one become, remodel become dummy variable already. Okay, then continue. The Y, and then split. Here you have one arrow, how CDF outcome. How CDF. What's problem to the value arrow? To the value. Yes, yeah, I have to run from beginning. Yeah, because I didn't start from beginning. Okay, now it's clear. Yeah, conversion. Okay, still the problem. SDF. What is idea? Hmm. Oh, I disabled this conversion variable. Yeah, so this should be enabled. Yeah, so now should be no problem. Okay, now it's great. So we can see, yeah, the the remodel become Boolean before it's the object of the summary variable conversion. Okay. Finally, yeah, there's no reduction of the variable. We will use all the data. If you use the small data, just 1,000, then we can see the minimum value, the best group. So we enable this, then start beginning. Okay, do you have any questions?
No, not at this
Yeah.
point.
Okay.
No.
I will upload the video to the Blackboard.
Okay.
See you later. Yeah.
Thank you, Dr. Wayne.
Okay.
Thank
See you.
you.
Have a
Yeah.
good night.
A good night.
Good
Bye-bye.
night, you all.
You too. Bye-bye.
Bye-bye.
Yes. Okay. The minimum 9. Okay. See.